Hello friends, today I am going to discuss this problem. This was asked in Iit Jee 2016. This is advanced level problem. It was asked in paper 2 and this is supposed to be one of the toughest problems ever asked in the history of Iit Jee. So this is arguably the toughest problem ever asked in the history of Iit Jee. So let me explain the problem. It is given in the problem that there are two disks. This is disk. The smaller one, there are two disks. If you observe the situation from this end, then this is a circle. So actually this is a disk, and this also, if you observe it from this side, this is a circle. I have drawn the side view of the disks. So it appears to be like this, and this appears to be like this. This is one of the disks, and the mass of this disk is m. The radius is a, and this is the bigger one. Its mass is 4m and radius 2a. And these two disks are attached to each other through a rod which is passing through their centers. So they are rigidly attached to this rod which is passing through their centers, and this length is given to be L equal to root 24a, and this length, this distance between the centers of the two disks, is also given to be L equal to root 24a. And these two disks are rotating about their axis with angular speed omega. This is given in this direction, that is like this, and it is given that there is no slipping. So it's given in the problem that these two disks are placed over a firm surface, firm horizontal surface, this surface, and there is no slipping. So because there is no slipping and they are rotating in this direction, then they must move, their center of mass must move in that direction. That is, they must rotate about the z-axis like this. So this is a three-dimensional motion. I mean, not motion in a plane, so it's a general motion of rigid body. So the picture is like this: the disks are rotating about this axis with angular speed omega, which is given, and the entire system of the entire assembly is also rotating about the z-axis like this. Because there is no slipping at these 2 points. These 2 points are not slipping on the ground, firm ground. So this is the situation. Now they have given some options, and we have to pick up the most appropriate ones. So I'll read the options. One of the options is the center of mass of the assembly. This assembly. Also, it is given in the problem that the angular momentum of the entire system, of the entire assembly about this point O, is L vector. Okay. Now I'll read the options. So the first option is the center of mass of the assembly rotates about the z-axis with an angular speed omega upon 5, omega by 5, omega over 5. So we have to analyze whether this is the correct one. So I have already solved the problem. So I'll just analyze and discuss the problem to save time. So let us see the situation here. Because it is given that these 2 points are not slipping over the surface, so these 2 points are at rest. So if you extend this line, this is the x-axis, this is the z-axis, and y-axis must be into the plane. Okay, now because these 2 points are at rest, so if you draw an imaginary line like this imaginary line, then this must be the instantaneous axis of rotation, because these 2 points are at rest at this instant. So fine, this is the instantaneous axis of rotation. So it may be imagined that the entire system is rotating about this axis at this particular instant. There is rotation about this axis, because this is the instantaneous axis of rotation. This means that the entire angular velocity of the system must be in this direction, because at this moment this is the instantaneous axis of rotation. So we can boldly say that the net angular velocity is in this direction. So here I have written omega net. Omega net is in this direction. So we can imagine that the entire system is rotating like this about this axis. Okay. Now we can also split this motion into 2 pieces. One is the rotation of the system about this axis, due to which its angular velocity is omega, which is mentioned here. And also superimposed on this, we can imagine that the center of mass, which is of these two disks, which is somewhere between the two, suppose it is here, and we can also locate the position of the center of mass, because the mass of this disk is concentrated here, m, and the mass of this one, 4m, is focused here. So the center of mass will be somewhere here in between, and its location has already been found by me. It's very simple, but we can very simply calculate it by a very simple formula. So it comes out to be, the location of the center of mass comes out to be 4L by 5, and this distance is L, and then this is 4L by 5. So this entire distance will be 9L by 5, which is RC. RC is the position of the center of mass of the entire assembly. So we may imagine that the total mass of the system, which is 4m plus m, that is 5m, is concentrated here at a point, and the coordinate or the position coordinate of this point is 9l by 5. Okay, now coming back to splitting this motion into two pieces. One is the rotation of the assembly about this axis, due to which the angular velocity is omega, and superimposed on this is the rotation of the center of mass of the assembly about the point O, like this. So we may imagine that the center of mass is also rotating like this, with this radius in a circle of radius RC, like this. So due to this rotation of the center of mass of the assembly, the angular velocity will be in this direction. Angular velocity of the system will be in this direction, that is perpendicular to this line. So it will sprout somewhere in this direction, and calling it omega 1. Okay. Now let us also imagine that due to the rotation of the assembly about this axis, the angular momentum is L omega, which I have written here, and the rotation of the center of mass about this point O, due to this rotation, the angular velocity omega 1 is in this direction, and the associated angular momentum is this, which is L omega 1. Okay, now this entire motion, because the motion is slightly complicated, the system is rotating about this axis with angular velocity omega, as well as it is rotating about the z axis like this. So for the sake of simplicity, the motion has been split into two pieces. Fine, but as I have already told you, the net angular velocity must be in this direction. So this can be supposed to be split or decomposed into two components, omega 1 and omega. This is the net angular velocity, and these two are its components. So I have drawn a parallelogram here to make the situation very clear for you. This angle is theta, so this angle is assumed to be theta, so this angle is theta. And from it is given, and from this triangle, this is 90 degrees. So if this is root 24a, this is a, then from Pythagoras this boils down to 5a. Okay. Now if you consider this triangle, then from this triangle tan theta will be omega 1 upon omega. I have written it here, tan theta equal to omega 1 upon omega. So omega 1 turns out to be omega tan theta. But we have to find the angular velocity. In this part we have to find, it's given that the center of mass of the assembly rotates about the z-axis with an angular velocity omega by 5. So we have to find the z component of this omega 1. Omega 1 is the angular velocity of the, due to the rotation of the center of mass about this point O. So we have to find the z component. So it will be omega 1 cos theta. So the z component of this omega of the center of mass along the z axis will be equal to omega 1 cos theta. Just inserting the value of omega 1 from here at this point, at this position, it becomes omega tan theta into cos theta, and then tan theta can be written as sin theta by cos theta, so it eventually boils down to this omega sin theta. And sin theta from this triangle will be this by this, that is 1 by 5. So sin theta is 1 by 5, so it indeed turns out to be omega by 5. So this option is correct, so I put a tick over here. Now let us analyze the other options. This option says that the magnitude of the angular momentum of the assembly of about its center of mass is 17 ma square omega by 2. So let's analyze this one. So this is the angular momentum of the assembly, and this is the modulus notation. So the mod of the angular momentum about the center of mass, let me call it L omega, which is this one, L omega. How can we calculate this? By assuming that the assembly is rotating about the center of mass. So due to the rotation of the entire assembly about this axis passing through the center of mass, what will be the angular momentum? So the angular momentum, the formula for angular momentum is I omega. So due to the rotation of this disk, the angular momentum will be I1 omega 1, which I must have written here, I1 omega, and due to the rotation of this disk about its axis, the angular momentum will be I2 omega. I1 is, for a disk, it is mr square by 2. So I1 will be ma square by 2, and I2 will be 4m into 2a square by 2 into omega. If you calculate this, then it turns out to be 17 by 2 ma square omega, which indeed is the correct option. So this is also correct. Now let me analyze this one. And this option says that the option given was the magnitude of the angular momentum of the center of mass of the assembly about point O is 18 ma square omega. So let us find the angular momentum of the center of mass about the point O. So the center of mass is moving in this direction into the plane of the board, because this is the instantaneous axis of rotation. So the entire assembly can be assumed to be rotating about this axis like this. So definitely the velocity of center of mass will be pointing into the plane of the board. So let's assume that the entire mass is focused here. Then what will be the angular momentum of this point, this mass, about the point O, which I have written like this. This is the angular momentum of the center of mass, and this is its magnitude, and we are evaluating this magnitude about the point. We are evaluating the angular momentum of the center of mass about the point O, this about O. So it is, by definition, RC cross PC. PC is the linear momentum, and we are finding its magnitude, because this is the definition of angular momentum, R cross P. So PC is the linear momentum, which can be written as 5m into Vc. So you can see that it is emerging in the next step, 5m into cross Vc. So now what is the direction of RC vector? This is the direction of RC vector, and the Vc vector is into the plane of the board. So the angle between RC vector and Vc vector is 90 degrees. So therefore, in the next step, it becomes like this: RC into Vc into sin 90. Sin 90 is 1, obviously. Then the next step is this, and then let us find the value of Vc. Vc will be very interesting, because definitely Vc is in this direction, and because this is the instantaneous axis of rotation, so we can imagine that the center of mass is rotating in a circle whose center is somewhere there on the instantaneous axis of rotation. So center of mass is rotating like this at this moment. So the radius of the circle which the center of mass is traversing is this length. So this length will be from this triangle this length will be, this is RC, so this length will be RC sine theta. So the velocity of the center of mass will be this length into omega net, because if you assume that this is moving in a circle, then the velocity will be r omega. So it will be this distance, r will be this distance, which is RC sine theta into omega net. So here it is, omega net. This r omega. R is RC sine theta and omega is the net angular velocity. So in the next step, it becomes like this, because omega net is equal to omega by cos theta from that triangle. And then sine theta by cos theta is tan theta. Now the next step will be, I have inserted the value of RC here. And then if you plug in the values of tan theta is how much from that triangle? Tan theta is 1 over root 24. So if you plug in the value of tan theta and plug in the value of L, which is root 24a here, then you will get this expression. But you will not get 81 ma square omega, which is mentioned in the option. So this is the wrong option. Okay, now let us analyze the last one, which says that the option says that the magnitude of the z component of L vector is 55 ma square omega. So we have to find the magnitude of the z component of the angular momentum. So how to find the magnitude of the z component? I found it here. This is the angular momentum along the z-axis, its magnitude. That is the angular momentum, net angular momentum along the z-axis. So in order to find this one, this component of the angular momentum of the assembly, we split this. In this, we take the component of this L omega 1 along the z-axis. So it will be L omega 1 cos theta. And the component of this L omega will be in the downward direction. It will be L omega sine theta. So the net angular momentum in this direction will be L omega 1 cos theta minus L omega sine theta, which I have written here. Okay, now L omega 1, we have already calculated the value of L omega 1 here. Now we put this value here. We have also found L omega here, which is 17 by 2 ma square omega. So we put this value here, and then we get this expression. After this, we plug in the value of cos theta from that triangle, which is this by this, and we plug in the value of sine theta from that triangle, which is 1 by 5. So if you calculate this, it eventually turns out to be 76.06 ma square omega and not 55 ma square omega, which is mentioned in the option. Definitely this option is also wrong. So I hope I have analyzed the problem for you, and I hats off to those who have successfully attempted this problem in the intense condition of examination. Thank you very much.